everyone. So we are studying currently the sensor terminologies. To some extent we have covered most of the sensor terminologies. Today again we will see some of the sensor terminologies which are again very important. But before that, let's see what we have studied in the previous lecture. So we started with selectivity, and we now know that selectivity is very important, especially for chemical sensors, because if you have a certain molecule that you want to detect, and if that molecule is not selectively or specifically reacting with the sensing active material, then you will find that there are a lot of interference from the other molecules as well. Now in this particular aspect, there is a catch. For example, you have a material, say A, which you would like to detect, and this particular material is available in blood. You have developed a sensor to detect A, so you have to ensure that any other material present in blood is not reacting with the active material of the sensor. However, if the sensing material is to some extent reactive to a material B which is not present in blood, then you may not need to that much, you don't need to be that much worried, because the sample that you are giving is blood, and in blood B material is not present, right? So in that aspect you can say that your sensor is very selective when you add blood sample, although our target should be the reaction that is happening is specific to A and is very specific to A only. However, if there is any other material which is, say, very close, the chemical composition of that material is very close to A and can react with the active material of the sensor, but is not present in the sample that you are introducing for sensing, it is to some extent okay. I repeat, just to avoid the confusion, if your sensor is very selective to material A and also to some extent reactive to material B, but material B is not present in your sample that you introduce, then you can use the sensor for your application. Okay. However, our target, as I have said, is to utilize an reaction, chemical reaction, which is very specific to A only. There should not be any other interference. But this is something that I wanted to mention, that's why I am saying. Okay. The next parameter is repeatability. So I already have said repeatability is something that is related to a single sensor. If you have a sensor and you start measuring with that sensor, then you take the same sensor for second measurement, third measurement, fourth measurement. If you find that all these measurement values or output that you get from all these measurement values are same or repeatable, then you can say the repeatability is very high. Then we have seen reproducibility. Again, reproducibility is something that is very close to what we have seen in repeatability. So very close to repeatability, but reproducibility is something that we usually use for different batches of sensor. For example, if you have a sensor which you have prepared in batch 1, you have same sensor that you have prepared in batch 2. If both these sensors are providing you the same output for the same input value, then you can say that your sensor is reproducible. Then there is dead band. We already have said this is something where your sensor will stop working. If, as we have said, if you have an output characteristics of this sort, and then at certain point if the sensitivity is almost 0, then you can consider this as deadband, although if the sensor is responsive thereafter. So you get a deadband where the sensor sensitivity is almost 0 or very low. It's so low that you can't use it for detection. So for that particular sensor, this range will be known as deadband. Then we also have seen stability. Stability is something to do with mechanical property of the sensor, electrical property of the sensor, chemical property of the sensor. So if the mechanical property is not very suitable, you will find that your sensor is not mechanically stable. If you find that the chemicals that you have used in your sensor is not stable in the ambient condition, then your sensor is not stable chemically. So all these stability parameters are to some extent interlinked. If your sensor is not mechanically stable, you will find that the same is getting reflected in your electrical output. Okay, so stability will also play a role in deciding what kind of material and what kind of sensor you should make. Then we also have seen noise. So noise is something that we have said that it's an unwanted signal present in your sensor output. However, there are various types of noises. In almost all the sensor output, you may get noise to some extent, but you have to take care of that noise so that it doesn't degrade your output from the sensor. So in the system level, you actually can take care of the noise. Even if your sensor is to some extent noisy, if you make a system suitable for that sensor, you can still use that sensor. Okay, so in the system level, there are different components that probably you have studied in your analog circuits or other courses. For example, filters. So they actually help us in reducing noises if the frequency of your noise and your signal noise is very different, right? That we will see maybe in the system part of this course if we study that part at the later stage. So today we will also see two more very interesting sensor parameters. One is excitation. So excitation is the electrical signal required for an active sensor to operate. So for each active sensor, you need an external signal or electrical voltage or current to make this sensor work. So what I mean by that is, for example, if you have a sensor, if you have an active sensor, say thermistor, that thermistor itself cannot work. For that purpose, you need to provide certain bias or voltage to it, and then you have to detect the output from it. So obviously, you will not apply the voltage directly. Maybe you will apply the voltage using a circuit. That is a separate issue altogether, but the voltage that you are applying to make this sensor work is known as excitation. So if your excitation signal is not noise free, then you will find that your output is also not very good. What I mean by that is, if you are applying a voltage which is noisy, that is the excitation voltage that is noisy, you will find in the output also you get the same sort of noise until and unless you use some other circuitry to suppress that noise. So usually we try to apply a high quality excitation signal to sensors just to avoid any sort of disturbance in the output. So excitation signal is very important. The other parameter that is again very important is dynamic characteristics. So a sensor may be characterized with a time dependent characteristics which is called a dynamic characteristics. To some extent you already have studied dynamic characteristics in your control system or maybe analog circuits to some extent. What does that mean? It shows the transient phase of your sensor response. For example, if you have a sensor and then if you start characterizing the sensor with respect to time, you'll find that almost all electronic devices, including sensors, take some time before it reaches to the steady state. So once you apply, or in other words, I would say once you turn on the device, you'll find that the device response in the very beginning at t equal to 0 is not stable. It takes some time before it reaches to a stable response at t equal to t1. And this phase is very important, okay, and this is what determines your dynamic characteristics of the sensor. So almost in all sensors you will find that initially the sensor is in a transient state and eventually it reaches to a steady state where your response is steady. Steady meaning not changing with respect to time. Okay. Now usually this timeline is in, say, microseconds, sometimes it's in milliseconds. This can also be in seconds. It depends on the sensor or device that is under consideration. But we also need to understand these characteristics to operate a sensor properly. Sometimes you'll find that the combined effect of your sensor's transient response and your circuit's transient response. So a combined effect of your sensor's transient response and your circuit's transient response may cause oscillation. That is the worst case. Usually it causes delay, but sometimes it may cause oscillation. So similar to the sensor, all system also have a dynamic characteristics. You probably have seen that in your control systems. If you have a control system and then if there is a sensor associated with it, the combined effect of both sensor and your system may cause delay, that is the best case, or sometimes it may cause oscillation, that is the worst case. If it is causing oscillation, then you have to take care of it. That's why dynamic characteristics is so important. Okay. So probably in many of the electronic gadgets you have seen, once you switch on the gadget, the gadget takes some time before it shows you the output. For example, if you take a example of a printer, okay, once you switch on the printer, it takes some time before it starts printing. I mean, there are different other reasons behind that. One of the reason is there is a warm up time for that. I mean, in case of printers, there might be some other concerns. For example, the heating and etc. is also associated with it, but a portion of that entire delay is for warming up the entire system. Okay. So the warm up time for a sensor can be very short or considerably long based on the sensor working and environment. You may find that this warm up time is not constant throughout, it varies. Okay. So similar to control system, a sensor system input output dynamic characteristics can also be described using a constant coefficient linear differential equation. So the input output dynamic characteristics of a sensor can be explained or described using a constant coefficient linear differential equation. This type of equations you also have seen in case of control system, which is known as transfer functions. So for many of the sensors you will find that equation is zero order function. So what I mean by that, maybe the dynamic characteristics is also linear, that is y equal to mx plus c, right? But in certain cases you will find the order of that function is even higher, maybe first order equation, second order equation. If the system is complex, then it can be also third and fourth order equation. Okay. Now the order of the differential equation depends on the energy storage system associated with that. Even in case of control system, you may have studied that the energy storage system is somehow related to the order of that transfer function, but in this case also it's it's more or less similar. For example, if you take an example of a temperature sensor, we have thermal storage capacity in almost all temperature sensors. What I mean by that, once you put the temperature sensor or expose the temperature sensor in a heated situation, you will find that this sensor has certain sort of thermal storage capacity. That is also known as thermal capacity. So that particular thing probably will study a bit more in detail in the thermal sensor part. But as the temperature sensor is associated with the thermal capacity, you'll find that the dynamic characteristics of thermal sensor or temperature sensor is first order equation. Similarly, if you take an example of a accelerometer, you'll find that accelerometer has two different storage system. One is mass, another one is spring. Because it's a MEMS device, it has a mass associated with it, it has a spring associated with it. Just to give you an idea, because you probably have not seen the structure of a accelerometer, so I'm just drawing it here. So usually an accelerometer has a say metal plate in the bottom, then it has a mass which is connected using a spring. Okay, so this is the spring part, this is the mass, and then you have metallic electrode at the bottom. So if the entire this system is metallic and you have another metallic system here, so both of this will create a capacitive effect. Now once the entire system is under acceleration, say the entire system is placed on a system which is under acceleration, then this mass will start oscillating, right, up and down, and when it oscillates, then the capacitance of the entire system will vary. Now the change in the capacitance can be calibrated with acceleration. This change in the capacitance can be calibrated with acceleration. So in this case, you have two storage system, one is mass, another one is spring. So the dynamic characteristics of an accelerometer will be a second order equation. Now I hope you know why mass and spring can be considered as storage system or storage component. Maybe in your class 12 you already have studied that Q equal to CV. So just I am trying to give you an idea why we say the same thing. So V equal to 1 by CQ, and in case of spring, you know, force equal to K into X, where X is the distance, right? F is force. So in this case, you can see that 1 by C is almost equivalent to K, the spring constant. So your spring or the electrical component associated with spring is a capacitor, which is a storage device. Similarly, in case of mass, we know that F is equal to M into A, that is M into dV by dt, and we also know V is equal to L di dt, right? So in this case, you can see that the electrical component which is equivalent to mass is a inductor. So mass can be compared with an inductor. So that is also again a storage device. So in case of a MEMS system, you have two energy storage components. Okay, so you have a second order dynamic characteristics. So one has to figure out what is the dynamic characteristics or equation associated with the dynamic characteristics in order to understand the entire sensor system. Now let us see how it actually affects. For example, your amplitude in this case, in case of an transient system, your amplitude will be a function of frequency. And these information you have studied in case of analog circuits as well, in case of a control system as well. And we usually consider that minus 3 dB point is the one beyond which we should not use our device. Why? Because in this case at least you can see the amplitude is decreasing with the increase in frequency, and minus 3 dB point is the point where your amplitude is reduced to the 70% of the maximum output. I repeat, minus 3 dB point indicates where your sensor output, maximum sensor output is reduced to 70% of the maximum output. So, it is reduced till the 70%. So, 30% reduction has been done. And why this minus 3 dB is giving you that 70% number? That probably you also have studied previously. Let me put it in this way. This is how you calculate, right? This is how you calculate the 3 dB point. So, if you calculate from this equation, you will find x is equal to 0.7. You can do that calculation, you will find that x is equal to 0.7, that is 70%, right? So, minus 3 dB point indicates where at what frequency your maximum amplitude has reduced to the 70% of it. Okay. So, usually we consider this as a cutoff frequency. Beyond that frequency, we do not use the device because amplitude is reducing and you probably won't get a reliable result out of it. Similarly, in time response also, you will see the same. If say this is plot 1, in case of plot 1, you can see that initially the response is increasing, then it is reaching to a saturation level. And in time response, the amplitude can be given using that equation, S is equal to maximum amplitude into 1 minus e to the power t by tau. Tau is time constant, which is nothing but the multiplication of capacitance and resistance. So, usually what we do, we consider one time constant as the starting point of our device operation, because when you are t equal to tau, that is one time constant, this S will be Sm into 1 minus e to the power minus 1, and this value is 0.63, more or less 63%. So, after one time constant, the response of your sensor will reach to the 63% of the maximum response, and beyond one time constant it is still increasing. So, you can take one time constant as your cutoff. So, then in that case you have a lower limit associated with that, right? And if the response is reducing with time, in case of first curve it is saturated, in case of second curve it is reducing. So, in that case you have two different limits, one is upper limit, another one is lower limit. So, you have to operate the entire sensor in this range. So, it is very important that you first figure out what is the range of operation, okay? And the cutoff frequency in case of first order system is related to the time constant as mentioned over here. So, why this number 0.159? Basically, the equation is omega c is equal to 1 by tau. So, omega is nothing but 2 pi f c is 1 by tau. So, that will give you f c is equal to 1 by 2 pi into tau. So, this 1 by 2 pi is 0.159. That is how this number came. Okay. Similar to the amplitude, we also have to take care of the phase. Phase is something that gives you how much the response lags behind the input change. Okay. So, if there is a lag or too much lag between your input and output, then again that will get reflected in your sensor output, right? So, we also have to figure out what is the phase margin and what is the gain margin. I am not going in details of this discussion, because you probably have studied this in either control system or analog circuit course, and you can, based on phase margin and gain margin, you can figure out whether the system is stable or unstable. If it is unstable, then it will start oscillating of something of that sort, right? So this particular discussion is required if you work with the dynamic response of a or transient response of a sensor. Okay, in most of the cases we work with the steady state responses only, but the dynamic response is very important again, because you may end up in getting a wrong result if you don't consider the dynamic response as far as the system perspective is concerned. Okay, so that is why I am giving you a idea about the dynamic characteristics of a sensor. Similarly, a second order response is specific for a sensor that responds with a periodic signal, and a second order system can be characterized using the resonant frequency. So resonant frequency is the frequency where the sensor starts resonating. Usually we don't operate a sensor in its resonant frequency. We either take a frequency which is well above or below, at least 60% above or below that resonant frequency, because that is the safe limit. Otherwise you may find that it becomes very difficult to control the sensor. However, there are certain applications where you will choose a resonant frequency, because in that case you may get the maximum benefit from the sensor. For example, say if you take an application of glass breakage, which is usually used in security systems. So you want to detect the glass breakage. In that case, you can use a sensor in the resonant frequency, because that has a particular frequency. Glass breakage thing has a particular frequency, and if you use the sensor in the resonant frequency, then a very small change also can be detected. So it's kind of a qualitative measurement, not a very quantitative measurement. So in that case, you can use the sensor in a resonant frequency domain. So this is some of these. There are some of the typical responses that is shown over here. If this is your stimulus, you'll find a response which is similar to A, which is kind of similar to the stimulus itself, so you don't need to worry about this much. If you find a response which is similar to B, then it has a certain cutoff, right? Beyond that you should use it, and before that it's like transient. In case of C, you have an upper cutoff, because beyond that anyways your amplitude is reducing, so you have to find an upper cutoff. In case of D, you have two cutoffs, one lower, one upper, so you should use your sensor between this range. And then in case of E and F, you'll find that the bandwidth itself is different. In case of E and F, one is narrow bandwidth, another one is wider bandwidth. So based on the response, you have to decide what kind of system you want to use, or whether to use that particular sensor in certain application or not. We also know there is another parameter which is known as damping. So damping can be of three different types: under damped, over damped, and critically damped condition. And based on the variation like A, B, C written over here, you can find out the damping factor. Again, this type of details you already have studied in control system, but for the sake of completeness, I also have kept that discussion in this course, which is related to sensors. So we have 3 take-home messages from these lectures, like all the other lectures. So combined effect of dynamic characteristics may influence the performance. So when I say combined effect, I mean the effect of sensor and the system. So usually you have dynamic characteristics for both sensor and system. So the combined effect may either introduce delay in your system, or it may also introduce oscillations in your system in the worst case. So delay is something that you probably observe in almost all the systems, but in the worst case it may also create oscillation. So one has to be very careful about that, as we have discussed in the beginning of this lecture. The second take-home message is the noisy excitation may cause noisy output. So if the excitation itself is noisy, so you'll see that the same is influencing your output, because excitation is something which is in the input side, or you may consider it as a bias. So in that case, if your excitation is noisy, the same will get reflected in your output as well. And then order of dynamic characteristics equation depends on the energy storage component present. So what I mean by that is, if there is one energy storage component in your system, you'll find that your dynamic characteristics is a first order equation. If the number of energy storage components are 2, in case of, as we have seen, the same in case of MEMS devices, in that case the dynamic characteristics will be of second order, and so on and so forth. So the order depends on the energy storage component present in your sensor or system. So in case of sensor, it's not necessarily energy storage components like capacitance, resistance, but the energy storage component equivalent, as I have said, say mass, spring, or say thermal capacitance, so on and so forth. Okay. So in the upcoming discussions, again we will see some of the sensor terminologies, and then we will slowly move to the sensor physics. Thank you.